Welcome everyone. So today we are going to talk about one of the more well-known theorems in the field of linear algebra, that is triangularity theorem, and also it has a very vast application. So before starting, since it is a very well-known theorem, you, uh, I would like any one of you may just suggest the statement that what the triangularity theorem states. After that, we will proceed. So this is the statement of the triangularity theorem. The theorem states that if T is a linear map from U to V, where U and V are vector spaces and U is specifically finite dimensional vector space, and there is no such condition on V, then there is the equation which each linear transformation satisfies, is that uh, dimension of the range space of T addition with the dimension of null space of T is equal to the dimension of the domain space. Or in other words, if you want to say this, is that rank of the transformation addition with nullity of transformation will result into the dimension of the domain space. So let's just dive into the proof. But before that, I want to ask you if anyone is aware that around which central idea the proof of the theorem revolves. Maybe my question if my question is not clear, then just let me know. But it is one of the well-known theorems in the field of linear algebra, which is used to prove the triangularity theorem. If anyone is aware about that, then just let me know. I will wait for 5 seconds, or else we will move towards the proof. Yes, anyone?
Cayley-Hamilton theorem.
Okay. Uh, yes. So the thing that I was talking about is that if you have any linearly independent set, okay, of a vector space, then you can extend it to a basis of that vector space, and uh, using that lemma only we will prove the theorem, right? So let us move to that. So we will start with the null space, okay, obviously. So we know that kernel or the null space is a subspace of the domain space, right? And we have assumed that the domain space is finite dimensional. So it is obvious that since kernel T is a subspace of U, then it also has to be finite dimensional. So the yes, so we are assuming that let dimension of the null space is n, uh, which is again a variable. Then since U is also finite dimensional, dimension of U is P, and here the obvious case is P is always greater than equal to n. So since kernel space is subspace of U, then we will get a basis of that set. So I am defining B is equal to U1, U2 up to UN be the basis of the null space. And since it is a basis, it is a linearly independent set in kernel T. But since it is a subspace of U, the set U1 up to UN, that is B, is also linearly independent in uh, the domain space U. And we know that if you have a linearly independent set in a vector space, then you can extend it to a basis of that vector space. So the same thing we will do. We are going to extend that set. Since we know that dimension of U is P, so I need P independent vectors, right? So here I have N, so I will move from N plus 1 to P. So now I have B1. Now I am naming it as B1. So B1 is U1 up U2, UN, and then moving ahead from UN plus 1, UN plus 2, and up to UP, which will form a basis for U. Now, consider the set of images of the vectors UN plus 1 up to UP. Okay, I am naming it as set A. So if I prove that A is a basis for the range space, okay, then dimension of range space will become P minus n, and that P minus n is equal to dimension of U minus dimension of null space of T. That is nothing but a bit modification of the statement that we saw. Here, just if you see the equation in the second line, we are just making dimension of range space of T as a subject. So we will get dimension of U minus dimension of kernel T. So if we prove that way, that is also equivalent to prove the theorem, right? So what I need to show is that this set A is a basis for the range space of T. Now, if I want to show that any set is a basis of a particular space, what are the two things I need to prove, okay, regarding that set? Anyone?
The set need to be linear independent and the set spans the vector space.
Yes, true. So I need to prove that the span of this set A will give you the range space of T, and this T of un plus 1, T of un plus 2 up to T u of up, these all vectors are linearly independent. Okay, so let us see how we need to prove. Yes, so we need to show that these two conditions. Now, to prove the first one, that is span of A is the range space. So we know that since B1 is a basis of U, so the span of B1 will give you the domain space U. Now, uh, since basis of U are this U1 up to UN and then UN plus 1 up to UP, those P vectors are basis for U, then if I apply T on these P vectors, then all these vectors will lie in the range space. Okay, so we have the range space is equal to this span of these vectors TU1, TU2 and up to TUP. But since we have shown that this U1, U2 up to UN, see here, the B is equal to U1, U2 up to UN are the basis of kernels of the T. So if I apply T on these U1 to up to UN, these n vectors, the image of those vectors is 0. See, you can see here T of UI is 0 uh, for all I running from 1 to n. So since we have range spaces spanned by these 1 to up to p vectors, but since these tu1 up to tun, these all vectors are 0. So ultimately the range space will, its span will restrict to these uh, tu1 un plus 1 to up to tup, this uh, span of these vectors only, and these are nothing but the elements of the set A that we defined here. So we have proved the part A, that is span of A is the range space. Now we need to show that it is these vectors un plus 1 up to up. These vectors are linearly independent. So just let us take this linear combination alpha n plus 1 up to alpha p. These all alphas are scalars, and tun plus 1, tun plus 2 are the elements of range space. See, I have taken a linear combination which is equal to 0. So what I need to prove is uh, that all these scalars are 0. Since T is linear, I can rewrite the equation 1 as T of alpha n plus 1 u1 plus up to plus alpha p up, but which is equal to 0. Uh, which means if I apply T on a vector, see, we know that un plus 1, un plus 2 up all individually are vectors, right? And multiplying scalar to that, it also remains the element of u only, and its linear combination is again an element of u only. So this entire linear combination is an element of u, the domain space. Now if I apply T and I get 0 as the resultant vector, then the entire linear combination will lie in the null space. But since null space is spanned by these n vectors, this u1, u2 up to un. So any element whose image is 0, it can be written as the linear combination of the basis vector of the null space, right? So the linear combination alpha n plus 1 un plus 1 up to alpha p up, it can be written as, it can be written uniquely as linear combination of these u1 to un, these n vectors, because they are basis for the null space, right? So now we have this equation. Let me just zoom it. See this one, alpha n plus 1 un plus 1 plus up to plus alpha p up, which is equal to beta 1 u1 plus up to plus beta n un, where beta i's are also scalars. So now what I do is I am taking alpha n plus 1 un plus 1 up to plus alpha p up, those vectors on the right hand side. So that step implies that I get beta 1 u1 plus beta 2 u2 up to beta n un, from which these linear combination will be subtracted and it will result in 0. But if you observe that u1, u2, un up to un plus 1, un plus 2 and up to up is a basis for U, which is the domain space. And since it is a basis, it is linearly independent set. So if this linear combination is 0, then all the scalars has to be 0. So we get that each beta i's and each alpha i's are 0. But in equation 1, we saw that this linear combination is 0. So using this equation 1, we conclude that these alpha i's are also 0. So we showed that A is linearly independent, and previously we showed that A is span of A will give you the entire space, range space. So we showed that A is a basis for the range of T. That is, dimension of range of T is nothing but T minus n, which is equal to dimension of U minus dimension of the kernel of T. And in this way we proved the theorem. Now we move towards the applications. So the first application is, if we want to check that given transformation is 1 1. So let us take a transformation U V to W be a map. If T is 1 1, then by definition we have T of U equal to T of V, which is implies U equals to V, where these vectors UV are from the domain space V. Since T is linear, sorry, since T is 1 1, then we have T of 0 is equal to 0, right? And kernel T will only have a 0 element, and we know that the dimension of 0 space is 0, right? Also note that the range space is a subspace of the codomain space. So dimension of range space will be always less than or equal to dimension of the codomain space. Now using the equation of the now we use the equation obtained by triangularity theorem. We get dimension of V is equal to dimension of kernel T plus dimension of range space, which will be always less than or equal to 0 plus dimension of W using the above argument. So here, from here we see that the necessary condition for T to be 1 1 is that the dimension of domain space should be less than or equal to dimension of the codomain space. Another application is that if we want to check that if T is onto, what we can do is, if since T is onto, we know that image of the space, image of the domain space is the codomain. That is, range space is equal to the entire codomain, right? So dimension of V is equal to dimension of kernel T plus dimension of range of T. Now we know that dimension of kernel space is again a non-negative quantity. So this equation is always greater than equal to the dimension of uh, codomain space. So from here, from this argument, we come to a conclusion that the necessary condition for T to be onto is that dimension of T, dimension of the domain space must be larger or equal to the dimension of codomain space. Here are some examples that you can look at. Uh, Based on the above argument only, I have constructed them. And yes, these were the applications of the Penalty theorem. And yes, these are the references. There is a YouTube video on the channel of Professor Kumaresan sir, and in that he beautifully explains the granularity theorem and its applications. And from there only, I have taken the reference. And yes, this was my presentation. Thank you, and have a nice day to all of you.